All right, this is the second part of 6-6. And now we're going to look at what if we're representing this unit vector not from the origin? What if it's somewhere out in the space of the Cartesian coordinate system? So if we have this starting point here and this ending point here, then representing this with our unit vectors I and j, we would have x2 minus x1 as our coefficient on I and y2 minus y1 on our coefficient of j. And that's how we're representing this vector here. So it says let v be the vector from the initial point p1 to 3, -1, and terminal point p2, -2, 5. And we want to write v in terms of I and j. Now if you wanted to graph this, you could. You could just draw a quick sketch of these points. You don't really need to. And -1. So that's p1, and then -2. And 1, 2, 3, 4, 5. So this is our start, this is our end, this is vector v. You can do that. I don't think it's necessary. V you can write as x2 minus x1 on vector I plus y2 minus y1 on vector j. And vector v then is going to be x2, which is -2 minus 3 on I, plus y2 is 5 minus -1 on j. And so vector v is -5I plus 6j. Now adding and subtracting vectors, it works pretty much how you would expect. The coefficients on the i's are added together and b's are added together. Subtraction works very similar. We can multiply a vector times a constant and it just gets distributed there. So all of those things work the way we would expect them to. Let's go ahead and look at a couple quick examples here. If we have these two vectors v and w and we want to find v minus w, -3w, and 4v minus 2w, we can do that. We have 5I plus 4j minus 6I minus 9j equals -I plus 13j. If we have -3w, that's just -3 times 6I minus 9j, and that gives us -18I plus 27j. And the last one, if we have 4v minus 2w, 4 times the v would give us 20I plus 16j minus 2 times w would give us 12I minus 18j. And then simplifying that, that gives us 8I plus 34j. Okay. And next page, we can look at vector addition properties. If I switch the order of them, it gives me the same answer. If I add u and -u, that gives me the 0 vector, which is a magnitude of 0. Scalar multiplication works the same way that we would expect. And finding the unit vector, this is going to be something a little bit different, but something we will use again. So if we want to find the unit vector in the same direction as v, so a magnitude of 1, we want to find the unit vector in the same direction as this, then what we would do is we're going to divide by the magnitude. So exactly what it says up here. For finding the unit vector that has the same direction as a given non-zero vector, we have the vector divided by its magnitude. So what we need to do first is find the magnitude. And it's actually given to us. So, or no, it's not. We want to find the unit vector in the same direction as this vector. And then we want to verify that the vector has a magnitude of 1. So what we want first is to find the magnitude of this vector. And that's going to be 5 squared plus negative 12 squared. And that gives us 13. 12 squared is 144, 5 squared is 25. That gives us 169, and the square root of 169 is 13. And so we want to find v over the magnitude of v. So that would be 5 over 13i minus 12 over 13j, and that's our unit vector in the same direction. But it asks us to do a second thing. It also asks us to verify that this vector, this new one, does have a magnitude of 1. So we need to show that the magnitude of v over magnitude of v is equal to 1. So 5 over 13 squared plus 12 over negative 12 over 13 squared gives us the square root of 25 over 169 plus 144 over 169, which is 169 over 169, which gives us 1. So we verified that it does equal 1. Now this last part at the bottom here says writing a vector in terms of its magnitude and direction. So here's where we're tying polar coordinates and vectors together. So the angle theta that makes v with the positive x-axis is called the direction angle of v. That's the direction of the vector. So we can use these relationships that we have here, make sure you know those, and we can rewrite our vector v in terms of these polar, this polar information here. So this is what we're looking to do. And this is called a velocity vector. It represents the direction and the speed of an object in motion. So it says the wind is blowing at 20 miles per hour in the direction of north 30 degrees west, and we want to express its velocity as vector v in terms of I and j. So let's first draw a picture of what this really looks like. We have this wind that is blowing 20 degrees in the direction of northwest. So if this is north, east, south, west, it's north and 30 degrees west. Okay, so that's the direction the wind is blowing. And it told us that it's blowing at 20 miles per hour. Now what that does is that tells us the magnitude. So the wind is blowing at 20 miles per hour. That's equal to the magnitude. And so it wants us to express its velocity in v in terms of I and j. So that's using what we just did above here. So v is equal to a I plus b j, and that would be the velocity vector v magnitude of v cosine of theta I plus I sine theta j. And that's going to be 20 cosine, and 90 plus 30 is 120, plus I sine 120. And then we can evaluate negative 1/2 and root 3 over 2, and that gives us v is equal to negative 10I plus 10 root 3j. And that's the end of the section.